What's up, all you badass programmers? So today I wanted to talk about the difference between arrays and linked lists, sort of at a general level. So today specifically, let's talk about integer arrays. So let's say this is a segment of memory, and we wanted to store 3, 4, 5, 6. So the key property of an array is that the memory provided for this data structure is contiguous, meaning all memory for this data structure appears in consecutive blocks of memory. So if this is memory address 0, then this would be memory address 4, because let's assume that integers are 4 bytes in this architecture. So this would be 4, this would be 8, this would be 12. Or sorry, 3, this is 7, and this is 11, because we're starting at 0. So essentially, oh wait, no, this is wrong. I had it right initially. So this is 0. Bytes 0, 1, 2, and 3 are the 4 bytes for 3. And then 4, 5, 6, and 7, 8, 9, 10, and 11, and 12. So essentially, an issue we might run into in the future is if we want to add new elements to the array, there's only so much room that this array was allocated. So you have to declare size initially. So if you expect a lot of inserts into this array, you will then have to reallocate a larger buffer. So let's say we wanted to insert 7 between the 3 and the 4. Well, we're actually going to have to copy this entire buffer over. So here's a 3, and we know we want 7 to be the second element. And now we have to copy the rest of the elements. So we see in the worst case, we're going to have to recopy the entire array if we wanted to write to the first element. So this is a large pitfall for arrays. But something that they are great for is that the way the processor reads from memory, they actually check something called a cache first. So let's say this is your memory, then this processor is actually going to read in a block at a time. So let's say that this is the CPU's cache. And I'm going to have to read every element of the array. Then I'm going to read in a consecutive block. Let's say in this case it's 12 bytes. But usually it's a much larger number. So 3, 4, and 5. When I go to read the first element of this array, it's going to be in my cache because I pulled in this entire block. Now when I go to read the second element of the array, we lucked out because it's already in our cache. So we actually don't have to make a expensive read operation from our main memory, or even more expensive from our disk. So all a cache is it's faster memory that gives you access to slower to access copies in main memory or even disk. So this is really convenient. And a really important factor of an array is that because it's contiguous, if you need to read multiple elements from the array, they probably are already in the cache. So you never have to go back to, so you minimize the number of times you have to go back to main memory. So the next block, if I want to read every element of the array, will be these next 3 consecutive blocks. And now notice that these last 2 bytes are junk. they don't actually have any data I actually want. So in this case, there's not really that much benefit. So essentially, the pros, you get fast reads. And in the cons, you get slow writes. Because in the worst case scenario, if you're writing to the first element, you're then going to have to copy the rest of the elements of the array. So now let's move on to linked list. So now this is a little different way to store our data. So let's look at our first element, which was 3. Now we don't just store the data element, we also store a second part. And this is a pointer, which is essentially a reference to another memory location. So this is telling us where our next element is. So this is usually called the next pointer. So let's say that we have our contiguous memory here as before. But now what we're being told is it's not until memory address 23 that we're actually going to encounter the next element. So let's say these are all addressed. And let's say that this is memory address 23. Maybe I should have made this 24 so it's a nice even number. So now this means our next element, which was our 4, is going to be at this memory address. And we store a little extra to tell us where our next element is going to be. So these are larger. Each element here might have been 4 bytes, but now we're actually storing another integer, which is the address of our next memory location. So we're actually storing 8 bytes in this case. So maybe a better picture is our same contiguous memory. And now it's 3. This is memory address 0. This is memory address 4. And we're told that our next element is going to be at 23. I'm just putting the at symbol here just so you know that this is a memory address and not just a regular integer. And then ... And then here is memory address 24 with the number 4. And then I'm not sure, maybe let's go 80. So our next element is the integer 4, and the next element after that is going to be at memory address 80. So why would we want to set up our data structure this way? Why would we want to store our numbers 3, 4, 5, 6 in this sort of messy, no real pattern kind of way? Well, the first pro is that it's memory efficient. Notice if I wanted a linked list of this size, let's say I want a list of 100 elements. If I don't have 100, if I don't have 100 times 4, 4 bytes per element, if I don't have 400 bytes of free memory space consecutively laid out in memory, then I'm unable to allocate an array. Whereas here, note, none of these elements have to be next to each other. All I needed was the size of a single element to be free. So in this case, 8 bytes to begin to start to build this data structure. So when allocating, the processor has to ask, are there n contiguous bytes free? Are there bytes all in a row for me to allocate this data structure? Whereas here, you're asking, are there n bytes free? Or maybe 2n, because you need to store the next pointer. So you might end up needing more storage in total for the linked list because you're storing the address of the next element. But here, it can also be a troublesome constraint on your memory. So this is just more memory efficient. You're going to be able to fit more it's more, so I guess you could make the argument it's maybe not more memory efficient because you have 2n. You need more memory for the linked list, but I would push back and say it just depends on whether or not you have a lot of free memory on your computer to begin with. So if you're already doing a lot of operations and storing a lot of files, then linked lists, I think, will be less likely to fail because you aren't constrained by needing the consecutive bytes of memory. So now the con goes back to what we were talking about with the cache. So note now that we're never getting lucky, or I should say we're rarely getting lucky. So let's say we grab this. We actually only captured one element, and so the more spread out our elements are, we're pretty much going to be hitting a cache miss with each element and having to reload our CPU's cache. So cons, it's very read inefficient. But it is write efficient. So these are basic ways to store a list-like data structure. What I would say is there are clever ways that you can combine these two. For instance, you can store pieces. Like, let's say you have linked list where each node is 3 elements long. So maybe then you have your next pointer. And then this is 3, 4, 5. And then it points on to the continuation of the next block. So then this way, it's kind of an array within each node, but it's still a linked list overall. So you're picking and choosing pros and cons so that it's more robust to the hybrid scenario. So you don't have to make a hard decision on, do I want fast reads? But then that's going to slow down my writes. So this kind of mediates the trade-off and makes it a lot less extreme. So thank you for listening. I hope you found this helpful. If you think I should clarify on anything or I messed anything up, please feel free to drop a comment and have a blessed day.